Unit 6, Chemical Bonding. So let's start with the introduction of chemical bonding. So a chemical bond holds two or more atoms together. It is a mutual electrical attraction between the nuclei and valence electrons of different atoms that bonds atoms together. Now remember, the charge of the nucleus is positive, and then you have the electrons which have a negative charge. So the electron clouds have a negative charge, and the nuclei has a positive charge. So why do atoms form? Why do bonds form? When atoms are independent particles, they have a relatively high amount of potential energy, and so that's except for the noble gases. So the other atoms, or if they're independent, they have a relatively high potential energy. So as a consequence of forming chemical bonds, there's a reduction that occurs in the potential energy. And this creates a more stable arrangement of matter. So with the exception of the noble gases, atoms have a tendency to want to bond to reduce the amount of potential energy. There's two primary types of chemical bonds. Ionic bonds, which is a chemical bond that forms between oppositely charged ions, so cations and cations, which have a positive charge, and anions. So over here it looks like I made a mistake. So here I should have said anions, which is a negative ion. Okay, let me write that down there. So, and anions, which have a negative charge. So you have a positive ion and a negative ion that are attracted to each other in ionic bonding. In contrast to that, you have covalent bonding. And this is a chemical bond that forms as a result of the sharing of pairs of electrons between atoms. And specifically, this is a pair of valence electrons. And so factors determine the type of bond formed between atoms. So there's a couple of factors that are involved. Both ionic and covalent bonds occur at different degrees as a result of the electronegativity of atoms taking part in bonds. Recall the electronegativity is the degree to which an atom attracts electrons. Electronegativity ranges from 0 up to 4, with fluorine having the greatest electronegativity of 4. When two atoms bond, the differences in the electronegativity between the atoms determine the type of bond and degree of either ionic or covalent bonding that occurs. The difference in the electronegativity, if you look at the difference, if it's 1.7 up to 3.3, you have the formation of an ionic bond. If it's 0 up to 1.7, you have the formation of a covalent bond. So let's take a look at this for a second. We'll go over this a couple times, but let's say you have atom A is bonded to atom B. And let's say the electronegativity of atom A is 1. And the electronegativity of atom B is 2. Oh, sorry, not 2, but let me do that again. Is 2. All right, what's the difference between the electronegativity of these two atoms? So 1 from 2 is 1. So the difference is 1. If you have a difference of 0 up to 1.7, you have the formation of a covalent bond. So because there's only a difference of 1 between the electronegativity of these two atoms, that means that the valence electrons are going to be shared relatively equally. They're going to be shared. They're not going to be transferred. There's not going to be a formation of ions. So this would be a covalent bond. Okay? Now contrast this with the formation of an ionic bond. So let's take this. I'm going to do, let's make two other atoms that are taking part in bonding. Okay? Let's say you have atom C and atom D. They're bonded together. Now let's say that the C has an electronegativity of 0.5. And let's say that D has an electronegativity of 3. So what's the difference between the electronegativity of these two atoms that are taking part in bonding? So 0.5 from 3 is 2.5. And we just said that if the electronegativity difference is between 1.7 and 3.3, then you get the formation of ionic bond. So what's happening here, this is going to be ionic bond. That means that an electron is going to transfer from the atom that has a lower electronegativity to the one that has the higher electronegativity. As a result, this atom here that lost this electron is going to be positive in charge, and this atom here is going to be negative. So then, because this now is a positive ion, this is going to be attracted to this negative ion. So when you have ionic bonding, you have a transfer of electrons that results in two oppositely charged ions. Okay, now a polar covalent bond, that's a covalent bond in which there is an uneven sharing of a pair of valence electrons between atoms. In a polar covalent bond, electrons spend more time around the atom having a greater electronegativity. There's not a transfer of electrons, but there is an uneven sharing of the electron. In a polar covalent bond, there is a difference in the electronegativity of between 0.3 and 1.7. In a non-polar covalent bond, it's a bond in which the bonding electrons are shared evenly between the atoms, and it results in an even distribution of pairs of valence electrons between the atoms. A non-polar covalent bond has a difference in the electronegativity of 0 up to 0.3 between the two bonded atoms. So let's look at some examples over here. Okay, sulfur has an electronegativity of 2.5. Hydrogen has an electronegativity of 2.1. If sulfur and hydrogen bond together, there's only a 0.4 difference in the electronegativity. As a result, you have a polar covalent bond. They're sharing valence electrons. However, the sulfur is going to have the electron near it more often than the hydrogen. Now let's look at this of sulfur and chlorine. Sulfur has an electronegativity of 2.5. Chlorine has an electronegativity of 3. There's only a 0.5 difference between the two. This again is going to form a polar covalent bond. Now chlorine and calcium, there's a big difference between the electronegativity of these two atoms. Chlorine has an electronegativity of 3. Calcium has an electronegativity of 1. There's a difference in 2 between the two. This is going to form an ionic bond. Now the last one, hydrogen and hydrogen. When you have two atoms, they both have the same electronegativity. Therefore, if they bond together, so that's going to be H2. If they bond together, there's no difference in the electronegativity. Therefore, the difference is 0. This is going to form a non-polar covalent bond. Okay? Now finally, metallic bonding. In metallic bonding, a chemical bond that results from the mutual attraction between the metal atoms and their surrounding sea of electrons. So electrons are not held tightly in metal atoms. So they actually share their electrons. So if you think of it this way, if I had a glass of water and I started putting little metal balls in there, think of the metal balls as being the nucleus of the metal atoms and the water being the sea of electrons. They all would be attracted to that sea of electrons, and that holds them together. And that's why metal is easy. You can bend it without actually breaking, because that sea of electrons, which is mutually attracted to all those metallic nuclei, they can move around without breaking. So that makes metal malleable. Okay? Now, if you look at some terms, a molecule, it's a group of two or more atoms held together by covalent bonds and is able to exist independently. A diatomic molecule is a molecule containing two atoms. And a molecular compound is a chemical compound whose simplest units are molecules. Chemical formulas. A chemical formula, it shows the type and number of atoms combined in a single molecule of a compound. So for instance, water, which is, we know water, H2O, that's a chemical formula. The subscript 2 here next to the hydrogen tells you that there's 2 hydrogens. There's no number here, but it's understood to be 1. It says if there's only one of an atom, one of an element in a molecule, you don't need to write the subscript 1. If there's 2 or more, you need to write it. How and why do covalent bonds form? A covalent bond forms when it results in the lowering of potential energy between atoms. Covalent bonds form as atoms approach each other. Electrons occupy overlapping orbitals, and there are both attractive and repulsive forces depending on the distance between the atoms. A bond forms between the atoms when there is a balance between the attractive and repulsive forces. Minimal potential energy results in a more stable substance that forms. So if you think of it this way, let's look at 2 hydrogen atoms. You have the proton of the hydrogen, and you have its electron. That's 1 hydrogen atom. Now I have another hydrogen atom here. So that's the proton. This is the electron. If these 2 electrons get too close together, their repulsive forces will actually push each other apart. But the electrons are actually attracted to the positive charge nuclei of each other. So they can't be too close, but they can't be too far. So there has to be a distance between them where the repulsive forces between these electrons is not so strong that it overpowers the attractive force between the negatively charged electrons and the positively charged protons in the nuclei. And so as a result, you can have a certain bond length that occurs. So a bond length is the average distance between 2 bonded atoms. Bond length is measured in picometers. And over here, it's hard to tell, but this is 10 to the minus 12. So I wrote that over here. And so this is 10 to the minus 12 written out. So you can tell that's a very small distance. Bond energy, the energy required to break a chemical bond and form neutral isolated atoms. The stronger the bond between the atoms, the greater the bond energy. Weaker, less stable bonds will have less bond energy. When a bond forms, energy equivalent to that required to break a bond is released. Octet rule. In octet rule, chemical compounds tend to form so that each atom gaining, losing, or sharing electrons, valence electrons, has an octet of electrons in its highest occupied energy level. There are some exceptions to this, but most atoms want to form the octet valence electrons. All right, so let me go back to this, to the octet rule. If you recall the noble gases, they have 8 valence electrons, and they're group 18. They are stable. Why are they stable? They're stable because they have 8 valence electrons. That's the most stable electron configuration for most atoms. Most atoms want to bond so that they achieve 8 valence electrons, and they can bond either through covalent bond, where they share valence electrons, or ionic bonding, which is the results or occurs when you have a transfer of electrons that results in opposite charged ions, and they hold the atoms together. So they'll go through either ionic or covalent bonding to form 8 valence electrons, and that's the octet rule. Lewis structure, formula in which atomic symbols represent nuclei and inner shell electrons. Dot pairs or dashes between 2 atoms represent bonds, and dots around only 1 atom represent unbonded electrons. So let's try this with, let me do an example with water. So we said that water is H2O. If I was going to represent that in the Lewis structure, what I would do is I would put an O, so that's the letter O, to represent the oxygen. And then what I'm going to do is I'm going to put a line here and a hydrogen. So this line represents a pair of valence electrons being shared between the oxygen and the hydrogen. And I'm going to put another one here. So this is another pair of valence electrons being represented by this line. And then I have 2 pairs of electrons. So I have 1, 2, 3, 4. So those dots are representing the unbonded electrons around the oxygen atom. So that's an example of a Lewis structure. So unshared pairs of electrons, they're not involved in bonding. Now you can have multiple bonds. So a double bond is a bond that forms involving the sharing of two pairs of electrons between atoms. And a triple bond is a bond that forms involving sharing of three pairs of electrons between atoms. So let me give you an example. So in organic chemistry, you'll find bonding between carbon atoms. And we can have a single bond between the carbon atom. And when I do that, I'm going to have, let me use hydrogens. We'll do hydrocarbons. So you have hydrogens. Okay. So this is a single bond between the carbon atom. Now what I could do is I'm gonna make this a double bond. So we had before just one pair of valence electrons. Now we have two pairs of valence electrons being shared. However, when I do that, I can't keep as many hydrogens because now what I have is 2, 4, 6, 8, 10 valence electrons between this carbon and its shared electrons, hydrogens, and carbon. And over here I have the same thing. So I need to get rid of one of these hydrogen atoms. So what I'm going to do is I'm going to erase the hydrogen atoms. I'm going to redraw it. Okay, because I don't need all those anymore. All right, so now we're going to have 1, 2, 1, 2. Now this is a hydrogen bond here. Sorry, a bond between hydrogen and carbon here and here. This is representing two valence electrons. This is representing two valence electrons being shared between the carbon. There's 2 here and 2 here. So now this carbon atom has 2, 4, 6, 8. And this hydrogen atom, which the most it can hold is 2, so it has 2 valence electrons because I'm sharing them between the hydrogen and the carbons. And the same over here. Okay, this is a double bond. Now I can have a triple bond, and a triple bond, it's a strong bond, but there's a lot of potential energy in there, so it's strained. So if an atom can go from a triple to a double bond, it probably will. All right, so now I'm going to draw another line between these two carbon atoms. So now I have 3 pairs of valence electrons being shared between these two carbon atoms. And now I'm going to have 1 hydrogen. Okay, so I have 2, 4, 6, 8 electrons being shared between the two carbon atoms and the hydrogen. And over here I have the same thing. Okay, so that's a triple bond. Now, we have polyatomic ions as well. And this is a group of collectively bonded atoms that together they have either a positive or negative charge. And when we talk about when we name chemicals and start writing chemical formulas, we're going to use polyatomic ions. Ionic bonding and ionic compounds. An ionic compound is made up of 2 or more atoms, cations and anions, that together their positive and negative charges equal. Ionic compounds often form crystalline structures, and I'll attach a video, or I'll post a video where I'll show you the structure of salt to give you a better idea of what the three-dimensional structure of salt looks like. So the formula unit in ionic compounds are represented by their formula units, which are the simplest ratio of atoms in a compound. The ratio of elements composing ionic formulas units depend on their charges. For example, sodium chloride has a formula unit of NaCl. The sodium has a positive 1 charge and the chlorine has a negative 1 charge, the sum of which forms a neutral atom. So if you look at chlorine has a negative 1 charge and sodium has a positive 1 charge. So I only need one of them. If I had, let's say I had, I'm gonna make up a fictitious chemical. If this had a negative 2, and this had a negative 1 charge. So A has a negative 2, and B has a positive 1. in order for there to be a neutral charge between the two of them, I'd have to, in other words, the sum of the charges should be 0. A -2 plus what equals 0? If I have plus 1, I have to have 2. 2 of the B atoms. Let me write that out clearer. So A, if that has a -2 charge, and B has a +1 charge, I have to have 2 B's in order for that charge, the positive charge, to cancel out the two negative charges of the A. So that's AB2. So if A had a -3 charge, then, and I had B, then I would have to have, if this had a +1, I'd have to have 3 of them. All right? And we'll talk more about that. It is the formation of opposite charge ions and the attractive between them that hold the atoms together. For example, chlorine has 7 valence electrons and sodium has 1 valence electron. When these two atoms bond, there is a transfer of 1 valence electron from the sodium to the chlorine that results in the chlorine atom having 8 valence electrons. When sodium's single valence electron is transferred to the chlorine atom, it then exposes the underlying energy level, which is a full shell, an octet. Ions in ionic compounds are often arranged in a crystalline structure which results in atoms having an optimal distance, that is the balance between repulsive and attractive forces. So I'm going to actually skip ahead and actually draw a picture of this occurring. Okay, let's look at an example of ionic bonding to produce sodium chloride. So NaCl. So I have a sodium atom here. All right, so that's this right here. And I have a chlorine atom here. Now, if you take a look at it, something you notice is that the number of electrons that you'll see, and specifically what I'm talking about is the number of valence electrons. In your sodium atom, you have 1 valence electron. So that's this right here. Now, if you look at the chlorine atom, you have 1, 2, 3, 4, 5, 6, 7 valence electrons. Now, if you recall, according to the octet rule, we want to have 8 valence electrons. So sodium, and remember that sodium is in group 1, and all the elements in group 1 have 1 valence electron. Okay, so it's in group 1. Chlorine, on the other hand, is in group 17. We take 10 away from the group number, and we have 7 valence electrons. And again, according to the octet rule, you want to have 8 valence electrons. So chlorine needs to gain 1 more valence electron in order to have 8 valence electrons. Sodium, on the other hand, would have to gain 7. But I can do something else. We can actually have an attraction, or a transfer of electrons. So I'm going to if I take this valence electron here, and I move it over here to the the chlorine, what will happen is I can have 8 valence electrons. So I'm going to put this electron here from the sodium. I'm going to move it over here to the chlorine. Now, if I count it, I have 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. And so that electron is gone. Now what I'm going to do is I'm going to erase this. Right? I'm going to erase this. So I no longer have that single valence electron. I've transferred over to the chlorine, and lo and behold, if you look now, I have 8 valence electrons for the sodium. So now I have 2 atoms that have the correct number of valence electrons. But I started out with sodium having 11 11 electrons. Now I lost one electron. That means that now I have 11 protons and 10 electrons. That means I have one more proton than electron, so this sodium atom is now positive. Now if I look at the chlorine, I started out with 17 protons and I started with 17 electrons. But now I added one more, so instead of having 17 electrons, I now have 18 electrons. That means I have one more electron than protons. So now I have a net negative charge for the chlorine. Now these are two different charged ions as a result. Sodium is positive, so it's a cation. And chlorine is now -1. It's an anion. So the negative charge of the chlorine is attracted to the positive charge of the sodium, producing sodium chloride. Okay, so that's how you produce sodium chloride. And essentially, this is what's happening when you form an ionic compound. You have a transfer of valence electrons. Why would you do that? Because you're trying to achieve the octet rule for the electrons, for the atoms. And remember, this is the noble gas valence electron configuration that I'm trying to achieve. So both of these now are much more stable than they were before. Now that we've looked at ionic bonding, we're going to move on to intermolecular forces. And there are a number of intermolecular forces, but we're primarily going to look at hydrogen bonding. So hydrogen bonding is a type of intermolecular force. And so this occurs between a hydrogen atom and a strongly electronegative atom. The hydrogen atom's positively charged nucleus is attracted to the unbound pair of electrons of the strongly electronegative atom. Hydrogen bonds form between hydrogen and water molecules. And there's different, you see this, hydrogen bonds forming between a number of, some other atoms, including nitrogen and hydrogen. And they play a very important role in water and how water behaves, but also in the formation of proteins. So the ultimate structure of proteins is influenced by hydrogen bonds as well as other bonds. In addition, you'll see hydrogen bonds involved in DNA. So they play an important role in biological systems as well. So let's take a look at the formation of hydrogen bonds between water, and then I have a short video that we can look at as well. So what I've done, I've drawn an individual water molecule. And recall that water is H2O. I have a hydrogen atom over here, and I have a hydrogen atom over here, and they're bonded to this oxygen atom. And that's what this line is. This line, it represents a pair of valence electrons being shared between the two atoms. And then I have these two unbonded pair of valence electrons. Now, oxygen has a relatively strong electronegativity compared to that of hydrogen. It's still covalent, but it's polar covalent. So the electrons are pulled towards, the hydrogen's electrons are pulled towards the oxygen more than they spend time around the hydrogen. As a result, the proton inside of each of those hydrogen atoms, it doesn't have an electron on this side of it. So the side facing away from the oxygen very often. So as a result, this side of the water molecule has a slightly positive charge. And then you have these electrons over here on this side, and there's no charge, no positive to shield it. So this side has a negative, a slightly negative charge. So as a result, If I have a neighboring a neighboring water molecule, the hydrogen of the water molecule is going to be attracted towards the the electrons of that oxygen. So let's say I got another water molecule. All right, so what I've done is I've drawn this hydrogen atom over here near or facing this electron because the negative charge of these electrons here are attracted to the proton in this hydrogen atom. And that's how you have a formation of water bonds, hydrogen bonds between water molecules. All right, so if I, let's take a look at that. And this helps explain some of the characteristics of water molecules because hydrogen bonds, they enable the water molecules to be attracted to each other. And that's how water, if it's going through a tube, like your blood vessels, the water is actually helps hold it together into a cohesive column so it can flow. Okay, I'm going to show a video that I have that I made using a model of the water molecule. Okay, so that is an example of hydrogen bonding. Another intermolecular force is the London dispersion forces. It's also called the van der Waals force. And this is a type of intermolecular attraction that happens from the constant motion of electrons, which creates instantaneous dipoles and induced dipole. A dipole occurs as atoms' electrons randomly move around the atom's nucleus, and sometimes they concentrate in a smaller region, concentrating negative charges, while other regions of the atom have a lower concentration of electrons, exposing the atom's positive charge. Thus, part of the atom is slightly positive, while another region is slightly negative, and it's described as a dipole. Since, like a magnet, it has, if only for a moment, opposite charges in different regions. This random dipole in an atom will induce a dipole in a neighboring atom, and as a result, the atoms are attracted to each other, resulting in a weak intermolecular bond. What does this actually mean? What it means is that you'll have in atoms, because the electrons move randomly, that sometimes part of the molecule becomes negatively charged, more so than other parts, and other parts become slightly positive charged, and that will cause atoms of neighboring atoms to be attracted to each other. In other words, because of the random movement of electrons, neighboring atoms will be attracted to each other, if just momentarily, and helps hold them in place. And so that's the other intermolecular force that we were talking about. The hydrogen bond, for the most part, is the one that's the most relevant in the biological sciences that we'll be talking about. Actually, what you'll be seeing in anatomy, physiology, and other biology classes, because it relates to the shapes that proteins form. Because when you talk about proteins in anatomy and physiology, you'll talk about the primary, secondary, tertiary, and quaternary structure. And those are all influenced by, I should say, the secondary, tertiary, and quaternary structures are all influenced to different degrees by hydrogen bonds. Now, the last part that we'll talk about is valence shell electron pair repulsion. And I'm just going to show this, just go over this a little bit. And I will add a YouTube video specifically on valence shell electron pair repulsion. And this influences, this is a concept or theory that actually influences the shapes that molecules will form. And that's important. The shape of a molecule has a very substantial impact on the function of that molecule. So what is it? So valence shell electron repulsion is a theory that describes how valence electrons of molecules are oriented as far apart as achievable, which influences the shape of the molecule. And then, so I'm going to go to the next page and actually show you the different shapes that can be formed. But remember, electrons have a negative charge. Okay? So if you have two electrons and they are close to each other, that's going to cause them to repel. Right? So if two electrons get too close together, they're going to repel. So there's a repulsion force between electrons. So electrons, they want to stay as far apart as possible. And that fact will determine the shape that a molecule will have, because the electrons want to stay as far apart from neighboring atoms. So let's take a look at this. So this is a chart that shows you the shapes of molecules, some of the shapes that you can have. And there's the first one is linear. The second was a bent shape. The third is a triangular planar shape. That's the third. The fourth is a tetrahedral shape. The fifth is a triangular bipyramidal. And the sixth is an octahedral shape. And so what here is on this first column, I'm showing you an outline that shows the shape that molecule will form. And then this column here is showing you a representation of different examples of molecules that show or they're examples of the shape. So this one here, the BEF2, is showing you a linear shape. So you have three atoms in this. You have the central atom, and these two atoms bonded together, and they form a linear or straight shaped. So this is showing you the molecule, the Lewis structure of that. And what you'll probably notice is that the fluorine atoms, they have 6 valence electrons. Okay, and these electrons in this fluorine atom here, let's say it's fluorine atom 1, and say this is fluorine atom 2. The fluorine atoms in the fluorine atom 1 want to stay as far away from the fluorine atoms in atom 2. So because of this repulsion from each other, it's going to cause this to have a linear shape. Okay, now if you look at the bent shape over here, you'll see this SnCl2, so zinc chloride. The electrons up here, these two electrons here, they're repelling these electrons here on each end. As a result, these electrons here are pushing these electrons here of the chlorine atoms, and that causes to have a bent shape. You can actually see it here. You have these two valence electrons of the tin. They're repelling the 6 valence electrons of the chlorine atom. All right. And then over here, the triangular biplanar. You have a boron trifluoride. You'll see the central atom here of the boron, and then these 3 boron atoms all bonded to that. These 3 fluorine atoms all bonded to that boron atom. And you see here, the Lewis structure, you can see how these electrons, they want to stay away from each other as much as possible. In order for them to be away from each other as much as possible, they're going to form this shape, this this triangular planar shape. And then you have this tetrahedral shape. You have this, so this is methane. You have this central chlorine atom, and these 1, 2, 3, 4 hydrogen atoms all bonded to that chlorine atom. And that's going to form a tetrahedral shape. Because the central carbon atom and these electrons that are bonded here, they're being shared between the hydrogens and the chlorine, they want to stay away from each other as much as possible, as far as possible. So that's what's going to influence the shape of that tetrahedral. All right, and this triangular bipyramidal. So this phosphorus pentachloride. It's a complicated shape, but you can see here how all these chlorine atoms and their valence electrons, they're going to repel each other as much as possible. And the octahedral, the sulfur and the 6 fluorine atoms, there were a lot of valence electrons on those fluorine atoms. They're going to repel each other as much as possible, and they're going to form this octahedral shape. And I'll make a video that shows some models that I have that make it easier to actually visualize these. But a takeaway message from this is that the shape that you form is a result of the electrons, the valence electrons of the bonded atoms, all trying to stay away from each other as much as possible. And that's going to influence the shape that it has. All right, and thank you, and thanks for your time watching this.